All right, here we go. So the last time we met on Monday, I got through most of section 8.2, but I didn't quite finish it up. I think I had we were doing some examples and I didn't quite have a good description written down on how to solve those. So I fixed those up and I think we're right in here, changing and shifting indices. Does it sound about right? I think so. We might have got through the first one, but let me just recap because this part's pretty important. The idea with changing and shifting indices, or reindexing, you could say, is the idea that you can take a power series and you can change the index variable or the variable of summation. And for example, you can change the n's to k's, you can change the n's to i's. The variable summation is it's a dummy variable, so it doesn't matter what you use. So most of the time when we get to the power series in the next section, you're going to switch everything to k's, okay? Because you're going to be given the problem in terms of n, and we're going to switch it to k's. Now, another thing you can do is you can shift the variable of summation. So for example, when n equals 0 for this one on the left, let's see if you guys can do this in your head. I want you to tell me what the first term is for that series right there. Plug in an n equals 0. What's the first term?
A0.
A0, right? Okay. All right. Now, this series next to it is actually the exact same series, but it's been reindexed. But it's the same series. It's equivalent. This one starts off at k equals 1. What's the first term in the series?
A0.
Yeah, it's the same. And in fact, all of the terms after that are the same. We could even reindex it so it starts at, let's say, I equals 2. You can see that if you plugged in I equals 2 here for the first term in the series, you also get A0. Okay, but that carries over to the second, third, so on and so forth. We've just kind of reindexed the series, and you can do this whenever you want. It doesn't change the series at all. It just changes the way it looks. All right, so we're going to be using this a lot when we do the power series method in the next section. So I know we probably already did this one, but let's do it again. We've got this this series given to us, and the exponent on the x is an n minus 2. So when we get to the power series method, we really want that exponent there. We want it to be just, we don't want it to be a shift. So why don't we do this? Why don't we change it to an x to the, or why don't we change it to a k? So in order to change it to a k would have to be equal to n minus 2. So that's the first thing we do. Oh, I forgot something. What happens if you plug in n equals 0? What's the first term in the series?
0.
Yeah, and what's the next term when n equals 1?
0.
Also 0, right? So is it okay if we just start the series off at 2? Shouldn't that be the same thing? You don't need the first two terms, right? And this is usually what we do with series. We usually start them off so that the first term is non-zero. Okay, so you're going to be doing that in the next section as well when we get to the power series method. Okay, so this is really what we're trying to do. We're starting with this guy and we want to replace that with the k. Now, if you want to change that to a k, you're going to have to let k equal n minus 2. All right, now if k equals n minus 2, we've got some things to change here. This will change into a k, but we also have to change the n minus 1, we have to change the n, and we also have to change the n equals 2. But that's really easy to get as long as we remember that k equals n minus 2. All right, if k equals n minus 2, the n minus 2 is going to get replaced with a k. All right, what about the n? Well, the n is going to get replaced with a k plus 2. Do you see why? If I add 2 to both sides of this guy, then I'll have n equals k plus 2. Okay, I also need to switch out this n minus 1. Okay, so in order to get an n minus 1 here, I would just add 1 to both sides. So n minus 1 equals k plus 1. And this one starts off at n equals 2. So you want to ask yourself, when n equals 2, what's k? Well, if n equals 2, then k is just 0. Okay, so we have everything to switch out. So we literally just switch them out with k. So the n minus 2 becomes a k. The n becomes a k plus 2. The n minus 1 becomes a k plus 1. And the n equals 2 becomes a k equals 0. Is that okay? All right, so what we've done is we've changed the way the series looks. And now the series has a general term x to the k. We're going to be doing that a lot in the next section. All right, let's try something else. All right, let's show this ugly thing on the left. Looks like this ugly thing on the right. So oftentimes when you have something like this, you start with a thing on the left, move it around until it looks like the right. So let's do that. Let's start with the guy on the left. So if we start with the guy on the left, we want to push that x cubed through first. So let's take the x cubed. When you push it through, it pushes through all the ends. It has nothing to do with the ends. And you push it right through to the x to the n. That's going to increase the power on x by 3. So that's our new left-hand side. Is that okay? All right. Now, you can see over here on the right, there's an n, right? Okay, well, look, we have an n plus 3, but I want to change it into an n. This is the part that you got to be a little careful with. Rather than changing the n plus 3 to an n, I'd like you to change it to a k. And the reason why is because it's going to get confusing having this n plus 3 and that n there. So what we'll do is we'll change it to a k like so. I'll show you how to do this in just a second. And then once you change it to a k, it's really easy to change it to an n. You just replace all the k's with n's. It's just a name, right? All right, so let's do it. All right, so if we want to change this to a k, that's our goal. Then that means we're going to let k equal n plus 3. We're going to use the same argument that we did above. Don't need that. Just use the same argument that we did above, and you can rewrite the thing that way. Actually, let's skip that step. We can go right to this one. Would you guys do me a favor and make sure that you can get this? Can you guys verify that that's correct? Delete. Where's delete? I'll give you a minute to go through and verify, okay?
Yeah, that works.
Okay, looks good.
Yeah.
I'm not writing in all the arguments here, but you know, yeah.
Yeah,
You
that's
guys-
what I got.
Okay, all right, good. All right, so now we've got the thing expressed in the general with a general term of x to the k. So the last part's super easy. Just replace the k with an n. And if you replace the k's with n's, that's what you get, and that is the right-hand side. Okay, do you see why we went to a k first and then went to an n? You see the reasoning? You could do it by skipping that part, but the thing is there's an n there and there's an n there. It gets confusing knowing which n you're working with. So it's much easier just to switch to a completely new variable and then at the end rename it. Okay, do you guys have any questions on this one? Okay. All right, let's try this one. All right, we're going to show that this equation implies that A0, A1, and A2 are equal to 0. And it also implies that this recursive relation is true for n greater than or equal to 3. Okay. All right, so Oh, by the way, a recursive relation is one that, well, in this case, it's not really recursive. Yeah, this one's not recursive. If that was an A, it'd be recursive. But let's show it's true regardless. All right, so here we go. I'm looking up at the top here, and what I'd like to do is combine these two series into a single series. Now, in order to combine two series into a single series, two things have to happen. First of all, the general term, they have to be the same. And they're clearly not, right? We've got an x to the n minus 1 and an x to the n plus 1. The other thing that has to be the same is they have to start at the same index value. So we'll do that part second. Let's focus on these parts being the same. That part and this part. All right, so we're going to do it the same way we did in the last problem. We're going to change both of them so that both of them are x to the k. All right, so to do that, for the first one, we're going to let k equal n minus 1. Is that okay? For the series on the left? We're going to let k equal n minus 1. Now, if you do that, can you guys verify that that's the series? Looks good,
Yeah.
Sebastian. Okay. All right. Okay, so we're halfway there. And now we're going to do this other one. Now for this one, I'm going to have to let k equal n plus 1. Okay, and if we let k equal n plus 1 for this one, we should get this series. We're not changing the series though, right? We're just changing the way it looks. Can you guys check that one? Is that one okay?
Yep.
Good. You guys have any questions on that? Doing okay? All right. Okay. All right. So now we can take our original equation here and we can rewrite it like this. You see, now they have the same general term, x to the k. Okay. Now, I'd like to add these series together, but I can't do it until their starting indices are the same, and they're clearly different. One of them starts at 0 and the other one starts at 3. So this is a really easy fix. All you really have to do is pull out the first 3 terms of this guy. Just pull it out to the side. So what we can do is take this series right here that starts at k equals 0, and we can break it up like so. Does it make sense why this is equal to this? Is that okay? Notice we're starting at 0, going to 2, and this one picks up at k equal 3. That's equivalent to this. All right, now what is this? Well, that's only 3 terms. K equals 0, k equals 1, and k equals 2. We could actually plug k equals 0, 1, 2, and 3 in there, and that's what we get, right? That's what that series right there is representing, this guy on the left. Is that okay? All right, so now we're ready to go. This was the whole point. The point was to get these ready so that we can add them together. All right, now in order to add the series together, they have to have the same general term, which they do, x to the k, and the indices have to start at the same value. And then one of the rules we learned about adding power series is you just add their summands, you add the insides together. That's it. So all we have to do is add these together. So if you add this guy plus this guy, they're like terms because they both have x to the k, so we just have to add their coefficients. You'll get this guy. Can you check my work there? Look okay?
Yes, sir.
All right. Okay, so now look, what is this thing? Well, that's just an infinite polynomial, right? It's got a constant term, an x term, an x squared term. This one picks up on the x cubed term, then x to the fourth and x to the fifth. And we know the infinite polynomial is equal to 0. We can use the vanishing coefficients theorem. But this should feel fairly intuitive. If you've got a polynomial equal to 0, doesn't matter whether it's an infinite polynomial. That means all the coefficients have to equal 0. So that means that a0 has to equal 0. I'll put this in to add in one more step. That means each of those has to equal 0, which means all of these must equal 0. Just looking at the coefficients. That part okay?
You wouldn't just subtract those to the other side?
Well, I'm using a theorem which says if you have a polynomial and the polynomial is equal to 0, our goal is to find the coefficients, right? The coefficients are the a0, the a1, the a2, and then the rest of these coefficients here. These coefficients. Okay, well, since the polynomial is equal to 0, then that means that the constant term must be equal to 0.
Yeah, that makes sense.
And then 2a1 must equal 0. And then, yeah, okay. All right. And all of these guys must also equal 0 as well, though, right? Okay, so we'll write that down too. And this is true for k greater than or equal to 3 because the series starts off at k equal 3. Okay, we'll just take this guy and solve for ak, the larger index, ak. And you have ak equals negative bk. B sub k minus 1 over k plus 1 for k greater than or equal to 3. And that was what we were trying to show. Okay, so I think we did it. That okay? All right, so there's no magic here. If you're really careful with the indices and you're really careful to organize, stuff in the right order and collect like terms, this actually pops out fairly logically, right? There's no magic or anything. All right, so we're going to be doing that a lot in the next section, so we'll get ready for that. Okay, so I think this is kind of where I left off. So there's some properties have this function, some functions have this special property that's really helpful when you're working with power series, and it's called analyticity. All right, so before we talk about it though, I'm going to show you a little diagram. Now we're going to talk about a function at a point. So let's say we have a function that's defined at a point, and it can be any function whatsoever. I don't care what it is, but it's defined at some point. We'll call that point x0. Now, out of all possible functions, some of those functions are continuous at x0. Not all of them, but some of them are. Now, out of all the continuous functions, some of those are differentiable, finitely differentiable at that point. Okay. Now, out of all those that are finitely differentiable, some of them are infinitely differentiable. Oh, by the way, let's go back here. Hopefully, you guys remember this one. Do you remember differentiability implies continuity from Calc 1? If you've got a differentiable function at a point, then it's definitely continuous at that point. It's because it's a subset of continuity. If you're in the green area, then you're definitely in the blue area. Okay. In other words, it's stronger to be differentiable than it is to be continuous. It's a harder quality to have to be differentiable. Well, some functions are actually stronger than finitely differentiable, and that would be infinitely differentiable. Okay, so let me give you an example. Oh, I think let's do one. Here's a function that is let's do this one, cosine of x. And then the point we're going to use is x naught equals, let's just pick a point 2. So my question for you is, how many times can we differentiate this function?
Infinitely many.
You can differentiate as many times as you want, and then you could plug in a 2 into all of those values, and it makes sense. So I would say that this is an infinitely differentiable function at 2. Okay, so that would lie in the orange area. Okay, let me give you one that's only finitely differentiable at x naught. Okay, so here's one.
Like the infinitely terms would be like the trig functions and log functions, right? That would be the only ones that are really infinitely differentiable.
Yeah, a lot of functions are, but even polynomial
Okay.
functions are infinitely differentiable. For example, if you had like, let's say x squared, it's a polynomial, right? Very simple one.
Mm-hmm.
The first derivative is 2x. The second derivative is 2.
2.
The third derivative is 0. The fourth derivative is 0. The fifth
Okay.
derivative is 0. So yeah,
Okay.
it exists, right? And then you could plug in points, but plug in a point, but they all exist. But here's one where you run into an issue. Let's say we had x to the 3 halves. Okay, and we're going to use the same point here, x not equals 0. I'm sorry, x not equals 2. All right, so that function's clearly defined at 2. So let's take the derivative. Okay, so the derivative would be 3 halves x to the 1 half. And then if you plugged in 2, it makes sense. You can take the square root of 2. However, look what happens if you take the second derivative. Bring the 1 half down, so you'll have 3/4 x to the negative 1 half. Well, if you think about what that means 3 over 4 square root of x, right? All right, does that derivative exist at 2? Can you plug in a 2 in there? Oh, wait a second. I messed up. This should be a 0. I meant to say 0 for this one. And I should have made that a 0 too. It doesn't make a difference up here, but it does make a difference down here. It works if you plug it in there. Makes sense. Works if you plug it in there. But does it work if you plug it in the second derivative?
No.
No, so this is only finitely differentiable. It's only differentiable in this case 1 time. So that would fall into the green area, but not in the orange area. Okay. All right, so the question is there something stronger than infinitely differentiable? And there is. Being analytic. If a function is analytic at x naught, it's actually stronger than being infinitely differentiable. In other words, if you have a function that's analytic at a point, you get everything else for free. It's the strongest. And it has something to do with power series. Here's the definition. A function f is analytic at x naught if it's equal, that's really important, to its power series on some positive radius of convergence about x naught. Okay. So if you have the function being analytic at x naught, you know that it's infinitely differentiable at x naught. You know that it's finitely differentiable, obviously, and you know it's continuous at x naught as well. You get all those for free. All right. So yeah, so this is kind of interesting because we want to figure out which functions. Maybe we can look at a function and just tell it's analytic, and then we get everything else for free. So like this function right here, 1 over 1 minus x, we know from Calc 2 that it has a power series representation, power series expansion, and it's equal to that power series expansion. That's something we proved in Calc 2. So because of that, we know that this function is analytic everywhere inside this interval. And the reason why is because it's represented by a power series in that interval. And that's what it means. It's equal to its power series on that radius of a radius and convergence about the point. All right, so how can you tell which functions are analytic? Well, polynomial functions are analytic, and they're analytic everywhere. Okay, so that means you get all of this for free. Rational functions are analytic on their domains. So this function here would be analytic everywhere except for 1 and -1. So everywhere except for 1 and -1, we get all of this for free. All right, transcendental functions. These functions are also analytic on their domains. So the domain of e to the x is everything. So that's analytic everywhere. Natural log of x is defined, its domain is x greater than 0. So it's analytic to the right of 0. Cosine x is defined everywhere. Okay, so it's important enough to know this because it's going to come in handy in the next section. The fact that a function is analytic means it has a power series representation, but not only that, it's equal to some power series representation on some positive radius of convergence. In other words, it doesn't just converge at the center. There's some interval around the center at which it converges. So another thing that's going to be helpful, if you have two functions that are analytic at a point and you have some constant c, then if you sum the two functions, that's analytic. If you subtract them, if you take a constant times one of them, if you multiply them, or if you divide them, all of them will be analytic. Of course, you can't divide by 0. That would be the one case where you don't have analyticity. All right, and then also if a function is analytic, then it's infinitely differentiable. I already mentioned that down here, but if you want to read the argument on why, it's right in here. It uses a bootstrap technique. All right, but we won't get into that. All right, do you guys have any questions about analyticity at a point? All right, it's a lot of new concepts, but when you hear the word analyticity, what in your head, you should be thinking, oh, the function has a power series representation and it's equal to it. All right, not all functions have a power series. Some functions have a power series, but they're not equal to it. So this is the strongest case. Like if your function's infinitely differentiable, it definitely has a power series representation. You could just use the Taylor series, right? You have all the derivatives, but just because you have all its derivatives evaluatable x naught doesn't mean that the resulting Taylor series will be equal to the function itself. All right, so I gave you a couple examples down there if you wanted to open them up and look at them. All right, so now we're going to build out what a Taylor series it is. You know, we already looked at Taylor series in 8.1, and I think it was appropriate because you guys have kind of seen it before. And I'm going to give you kind of the reasoning on where it comes from. A Taylor series is just a special case of a power series. Look, here's a power series right here. That's a power series, right? And the ANs are constants. Now, if you choose the ANs to be these guys right here, those are constants. Then what you have, that's your AN. Then you have a Taylor series. So it's just a special case. So the way these are derived are quite easy. You just use a little calculus, but let's say a function f is analytic at the point x naught. If it's analytic, it means it has an infinite number of derivatives. That's one of the consequences of being analytic. So what do? Well, since it's analytic, we know it has a Taylor series. It looks like so, about x naught. Let's differentiate this guy, and let's expand all the terms out. So, we're going to keep it condensed. So let's differentiate. So that would be the 0th derivative. That's the function itself. All right, let's take the first derivative. You just differentiate term by term. You notice on the left and the right, they look identical. The only thing that I changed is I changed n equals 0 to n equals 1. Why did I do that?
First term would have been zero
I
anyways.
meet her today. She's super nice.
Yep. The first term would have zeroed out anyways. So we usually get rid of the first term if it's zero. You always want the first term to be non-zero. So then we differentiate again. And then we get this guy. Remember, to differentiate, you just differentiate the inside where x is the variable. All right. In this case, the first two terms drop out like so. And then you differentiate again. In this case, the first three terms drop out. And you could do this ad infinitum. You could go up to, let's say, the jth order derivative. It would look like this. That would be your jth order derivative. The first few terms drop out up to n equals j. And you could keep on going like this forever. Now let's take all of these and let's evaluate them at x naught. So replace all the x's with x naughts. Okay, well, what happens? Well, what ends up happening is, let's see if you can plug them in. Let's take the first one. If you plug in an x naught there, all of the terms drop out except for the first one, which is a naught. You can see it right here. If you plug in an x naught here and an x naught there and an x naught there and an x naught there, all of these terms drop out and you're left with an a naught. All right, what if we were to do the same thing with the first derivative? Plug in an x naught right there. All right, now plug in n equals 1. What's the first term?
1 or n.
A1, right? But all of the next terms after that drop out, right? Okay, so we're just left with the first term, which is A1. We'll do the same thing here. Plug at x naught into this function. So that means everywhere that means we're going to replace that guy with an x naught. So what's the first term? Look at an n equal 2 there, right?
2a2.
Yeah, it's just 2a2, right? 2a2. And then we could do it here. Plug in an x naught into this function. We'll plug it into this one. If you plug in an x naught here, what's the first term?
Six A3.
Yeah, 6. And you see what's happening is you're basically doing a factorial here. That'd be 3 times 2 times 1. And remember, all the other terms drop off. So you're only left with the first term. So you can see the pattern. What ends up happening in general is you have a factorial times whatever your order derivative is. So third order derivative, you're going to get a 3 there for your index. Now, if we take these guys, remember our goal for solving these things is to solve for the coefficients. A0, A1, A2, A3, so on and so forth. So if we take each of these equations and we solve for the coefficients, A0, A1, A2, A3, this is what we get. So if we take these coefficients and we plug them into the original power series, this is what we have. And that's the Taylor series. That's what we studied in section 8.1. Do you remember that? Okay, so a Taylor series is just a special case of a power series. That's it. Let's see. Yeah, and by the way, when you find a Taylor series, it doesn't matter how you find it. You can find it in different ways. You can use different arguments. They're basically unique. You don't have to worry about it. If you find a Taylor series about a particular point or a power series about a point, there's only one, so they must be equivalent. If you got different answers using a different method, you get the same thing. For example, in example 2, we found that arctan of x was equal to this guy by integrating a geometric series. So that means if we were to find the Taylor series of this using the methods of section 8.1, we would also get this. So whatever method you use, it will be equivalent. All right, and Here's some common Taylor series that you're going to run across. You guys are going to have this on your final. Do these look familiar from Calculus 2? At least somewhat familiar, hopefully. What we have is our function over here, our functions over here on the left. By the way, each one of these is transcendental, so they're all analytic on their domains, right? 0 is in the domain of e to the x. 0 is in the domain of sine x. 0 is in the domain of cosine x. And 1 is in the domain of natural log of x. Therefore, by the definition of analytic, there must be a power series for each of these at those centers. So the power series for e to the x is that guy, which you could write in compact form like so. And the interval of convergence is everywhere. Usually we just don't write it in. If you don't write in anything, you can assume that we mean negative infinity to infinity. Okay, but I'll write it in here just to make it absolutely clear. All right, so there's some power series. By the way, these are also Taylor series, right? They're all equivalent. All right, and this one's a little funny because it's only valid between 0 and 2, not including 0. But it kind of makes sense, right? Natural log of x at 1. The furthest you can go to the left is you can't quite reach 0 because natural log of x isn't defined at 0. So the radius must be 1. So if you're centered at 1, you can go to the left and to the right. You can go out a distance of 1, not including the endpoints, and then you'd have to test the endpoints. Turns out 0 doesn't work because it's not defined, but 2 does work and it does converge. So, all right. I had a few questions about this section. So if you guys get stuck on number 8, you can look at that one, or stuck on part 3. You know what? I'll show you this one because this one was a little tricky. We're going to determine the I think it was radius of convergence, right? Oh, interval of convergence. This is one of your questions from your homework. Is this a series or is it a power series? And how do you know the difference?
The power series because of the x.
Yeah, if it's got a variable in there. Yeah. Yeah, if you were to expand this thing out, I know it looks like there's k's in there, but once you expand it out, you'd get this big long expression. There wouldn't be any k's involved. There's just x's, right? This is a function of x. That's what it is. Okay, so let's say we want to find the interval of convergence for the power series. So what we're going to do is we're going to use this. We studied power series and their intervals of convergence. The first thing you want to do is find the radius of convergence using this theorem right here, forcing the ratio test. Okay, once we find the interval on the radius of convergence, then we can just check the endpoints independently and we'll be done. All right, now in order to use the test, your power series has to be of the form n equals 0 to infinity an x minus x naught to the nth power. Now we have a little bit of an issue here because, it's a k. If it was a k, we'd be fine, but it's not. It's a 4k. So we have to fix this first before we can even apply the test. Okay, so we're going to use what we know about, changing indices to do that. All right, so I want this to be, let's switch this to an n. So I'm going to let n equal 4k. Is that okay? If I let n equal 4k, then that means, let's see, 4k equals n, 2k equals n over 2, k equals 0 goes to n equals 0. So I can rewrite this power series this way. Is that okay? Now I probably should have used a, oh no, we're okay. Yeah, we switched to n's. All right, so now we can use that forced ratio test. Are you guys following why we had to do this first? The ratio test applies if you have x to a variable, x to the n. It doesn't apply it when you have x to like a 4 times a variable. See, it only applies when you have x to a variable. By the way, the center is 0 for our particular example. All right, so we're ready to do the test. So we're going to take the constant sitting out in front of the variable term, an over an plus 1 absolute value, take the limit, and then we'll get the radius of convergence. So let's do that. Let's evaluate that limit. Here's your an term. We'll put that up top. And on the bottom, we'll put an plus 1. Just replace the n with an n plus 1. All right, now all you have to do is massage this thing a little bit, see if you can figure out the limit. So first of all, when you have an exponent with a 1/2 up there, that's really taking a square root. So the top looks like that. Is that okay? The bottom looks like that. Is that okay? All right. All right, what's next? Well, we have a square root. We're dividing where we're taking a square root in the numerator and the denominator, so we can combine them like so. And then 5 to the n plus 1, that's the same thing as 5 to the n times 5, right? So I can cancel the 5 to the n's, and I'm just left with the square root of 5, which, by the way, you don't really need the absolute values, right? In fact, you could have dropped the absolute values at the very beginning. Everything's positive in here, so we're not going to have any issues. And the limit of a constant is just the constant. Okay, so that means the radius of convergence for this power series, which is centered at 0. Can you guys see that? There's a -0 in there. I just didn't write it in. The radius of convergence is 1 over √5. That means we're going to start at 0. We're going to go to the left and to the right, a distance of 1 over square root of 5 in both directions. And within that interval, that's your, at least we know it's convergent within there. But we still need to know the endpoints. So the two endpoints would be positive 1 over square root of 5 and negative 1 over square root of 5. So how do you suggest we take care of these points? What are we going to do with these?
Plug them in for your x.
Yeah, exactly. What we're going to do, it's only 2 points, right? We're going to take we're going to take this one. We'll start with that one and we'll plug it into the original. Oops, keep going. We'll plug it in right here. Okay. And when you plug it in, you're going to get a series of constants. And then you're going to apply series tests to that. All right. Can you guys help me out? Let's name some of the series tests. What do you think?
B series.
B series.
Nth term test.
Nth term test. Okay. Alternating series test. Ratio test, root test, comparison test, limit comparison test, integral test, divergence test. So there's a lot of them. My computer just freaked out. Hold on. You guys still there? Okay. All right, good.
Still here.
Yeah, so you're going to want to review those from Calc 2. So hopefully you have some notes you can review, but if not, I posted something in your Canvas homepage under, I think, brush up material with red pen, black pen, and there's some examples of him going through a few different tests. Okay. Now, it's not a big deal to go through these, in detail, but it's important to be able to look at a series and tell what's happening with it. So we're going to do the same thing with this one. You're going to plug this guy in. So I'll show you the series test on both of them. So when you plug in 1 over square root of 5, which is the right endpoint, into the original power series, it becomes a series of constants. And you could simplify this. That 5 squared is really 25. And then this simplifies nicely. That's the series of the one terms. All right, so if you think about what this looks like, it looks like this. Right? All right, does that converge or diverge?
Diverge.
Yeah, there's no chance of this thing converging. If you just keep adding one, probably a grade schooler would know that that thing diverges, right? It's just, it doesn't, I mean, the terms don't even go to zero. So you can actually, I mean, one way to say it, it's you're applying the divergence test. If the terms don't go to zero, there's no way the thing's going to converge. So yeah, this one diverges. So we definitely do not want to include this guy in our solution. Okay, what about the other one? What about this one? Well, we just do the same thing. We take it, we plug it into our power series. It turns it into a series of constants, ends up being the same. So it diverges for the same reason. So that means that we don't want to include this guy either, neither one. So that means that our interval of convergence, I don't know why I wrote a row there, it's probably in my sleep. That means that this is our interval of convergence. Is that okay? All right. So yeah, be careful with these because you can't just use the forced limit comparison test right off the bat. You have to make sure that you just have a single index there, a single index variable. All right, let me fix that. All right, I'm going to pause. I'm going to give you guys a couple minute break.